Okay, everyone, now we're on to the examples of probability. So what we have here is called a contingency table, and if you recall from Unit 1, that is the case where you have multiple variables. So here you have gender identification, here you have political party affiliation, and you're comparing the two of them simultaneously. So you're trying, it's the reason it's called contingency table. It's not just males that are Democratic or Republican, nor is it just Democrats, let's say, that are male and female. It's multiple amounts of each variable. So what we are going to do to interpret this, remember, is where a row and a column intersect, this 405 represents the number of male Democrats, or you could think of this as the 235 female Republicans. And usually they, if to save time, they would give you a total, but if they don't, you always want to add these to get, in this case, 1250, or add vertically to get your totals there, and then they will reach the same overall total here. Now, the reason that's important, this here is your default denominator unless you're told otherwise. So, for instance, in part A, what's the probability you call a Democrat? That's just total Democrats out of total people. And that's where we get this answer here. Now, one thing I will say for AP testing purposes, you want to reduce your fraction. They're going to want to see that. I would suggest is using a calculator to do that, or doing, math enter after you've typed in the fraction. Or if you want to do a decimal, you just type it in and hit equals at least 3 decimal places, the nearest thousandth. All right, so that's just rule of thumb what I would do. Okay, so let's get back to just conceptually what's going on. This next one, what's the probability you do not call a male? So I wrote that formulaically. That's like saying 1 minus the probability you do call a male, and it's 1 minus that fraction. Some of you may have realized, isn't that just like saying you called a female? Yes, but if there were more than 2 variables, it would be best that you do this work right here. Okay, next one. Here's where we see that word or, and we have to be careful. It says, what's the probability you call a female or a Republican? Well, here's the total females, 1,080. Here's the total Republicans, 990. The word or does mean you want to add these, but you want to be careful because, as you can see, there is a situation where you have an overlap. There are 235. That number was used to create that 1,080, and it was also used to create this 990. You don't want to count it twice. So the way to avoid doing that is to add and subtract it, or just be savvy about it. Like if you have a contingency table, you could very well just say, okay, here's all the females. I got that from adding these two. And if they want Republicans, well, I'll just add 755. Why would I add 235 again? And that's really what you're adding right there. So if they don't give you a table, definitely use the formula way of doing things where you add and subtract their overlap. And in the end, that is the answer you'd come up with. Now, this problem I don't really like because it says within your first 5 calls, what's the probability you call at least one female? That really doesn't apply here because, again, the idea is that if you were calling people, it's probably without replacement. If you actually worked somewhere and were calling people, you'd probably cross off the name once you call them, and that would change the probability of it occurring each time. So this isn't really a perfect question. So I'm going to put a little bit of a face by it because it doesn't really work here. But let's say it was just percents. Usually if you're given like percents and you don't know the exact count of people that you're dealing with, you might be able to get away with this. So let's just say they tell you whatever this percent is the chance you call a female. What's the probability you call at least one? Remember, that's 1 minus the probability of you not calling a female. That's what I actually circled in green, raised to the 5th power. So again, that doesn't really apply in this case. This would really only apply if you are working with independent situations, replacement is happening, or you are given a percent to start off with. So it really doesn't apply here. And that is, again, one I wouldn't really worry about. I want you to know how to do at least once, but not in this context. Okay. The next one says, this is conditional probability. What's the probability you call a male given that? And again, there's that magic word, given that. When you see given that, whatever comes after it is your denominator. And that's what we wrote right here. So they're basically saying only look at Democrats. What's the probability you select a male? And that's why we have this as the denominator. And then it's males out of that. Now, here's that word disjoint. We know that means mutually exclusive. That means they don't intersect. Well, in this case, with a contingency table, they all intersect. There are male Democrats and male Republicans. There are female Democrats and female Republicans. So none of them are really disjoint in this case. So for them to say, are being female Republican disjoint? No. There is overlap. There is, as a matter of fact, 235 female Republicans. Okay, now this part, do you believe they're independent? Now, independence, if this was the AP test, this is where you'd be doing hypothesis testing. Like you'd probably be doing something more in depth. But in this situation, we're checking this. Is the probability of one thing the same as the probability of that given A? Now, what does that mean? Well, that's like saying, what's just the probability you select a female? You could have picked male. We just picked female for this example. What's the probability you select a female? It's 0.482. And I would find the decimal here because it's going to be hard to compare huge fractions. Okay. Unless these are a match, they're not independent. Okay? If they're really close, like if you got 0.49 right here, maybe you'd argue that there's a chance they're independent, but this data suggests they're not. And what you see here is that they're definitely not independent. So what's happening here? The probability you choose a female or call a female is 0.482. Now, if these were truly independent, the probability of me calling a female given that they're Republican or the probability of calling a female given that they're Democrat should be the same. And you don't have to do both. You could have just picked one political party. So I could have just said, what's the probability I call a female given that I'm selecting only from Republicans? These two numbers do not match. Therefore, I can argue being female and being Republican are not independent. Now, just to show the work, I also did it for Democrat, and the same argument comes through. If there's a 0.482 probability of calling a female, the probability of choosing a female given you're only selecting from Democrats, if they were truly independent, they would be the same, and they are not. All right, now you can see down here, this is just a different way you could have phrased it. You could have said, what's the probability someone's Democratic, and then said, what's the probability someone's Democratic given I'm only selecting from females or given I'm only selecting from males. Long story short, you're not getting the same answers. Therefore, this suggests that gender and political party are not independent. Okay, moving on. This, again, makes more sense with this at least once, because it says our friend Jesus Shuttlesworth from He Got Game can shoot and make free throws 88% of the time. It's not saying, it's just saying 88%. So because that's his free throw shooting percent, we can use that because and again, you might argue, well, if someone makes a shot, maybe they're not as likely to make it the next time. We're assuming each free throw is an independent event. So if I ask what's the probability he makes 3 consecutive free throws, it's just 0.88 to the third. What's the probability he misses at least one? That's like saying 1 minus the probability he doesn't miss at all to the third power. So that's what's going on here. And again, that makes more sense than our previous example because this was given as a percent. This example here, choosing dorms, this is a without replacement because if you're choosing who gets to be in a dorm, there's 12 choices. Let's say the selections are in a hat, which is what it says right here. If there's 12 of them remaining and 3 of them are for what's called a gold hall, if you choose, there was a 3 out of 12 chance. Then your friend chooses after you. Well, there's 1 less thing in there, so that's 11, and there's 1 less gold hall, so that's 2, and you'd multiply them. So that would be a case that either these events are dependent are without replacement. You're not putting your selection back in the hat. You're keeping it. Okay, you may encounter a Venn diagram. Venn diagrams, my advice to you is to always start with their overlap. So I would always start in the intersection. So this is asking about people who own dogs or cats or both. If 16% own both, boom, put that in the middle. Now, what you notice I did, I took the dog and the cat numbers and subtracted that overlap. That tells you the amount of people that exclusively like dogs or cats. And that's important because this 16% in the middle came about as part of dog and part of cat. Like it came from those. So if you want to know exclusively who likes one animal or the other, or rather owns one or the other, you need to subtract that overlap off. So in the first case, we drew our Venn diagram. Something else to remember, when you get your exclusive dog, exclusively cat in both, you don't want to forget about this empty space. It's called, I guess it's like the complement, if you will. It's where neither, they own neither of these two. That's where it's important that you know what the unique to dog and unique to cat number are, because you have to subtract those from one in addition to the both circle. Okay, so you'll see here, what's the probability someone owns a dog or a cat? Well, that's like saying dog plus cat minus their overlap. That's where 0.37 comes from. Now that we've done the work, we can already tell who owns only a cat is 11% and neither is 63%. All right, moving along here. Now, I will tell you this. The contingency table aspect of these questions, I doubt you're going to have... You would never have to make that. I'm telling you right now, you're not going to have to make it. You would really just be doing the tree diagram. So if you're kind of looking at this table and you're like, where did that come from? This is just me translating the tree diagram into a table to help you. You do not need to do that, and we're not even going to like look at where it came from. It basically came from the tree diagram. So what's going on in this problem? This is an antibody test where it says if someone has antibodies, a test returns a positive result 80% of the time for those who actually have it. However, it also gives a false positive for those who don't have it 30% of the time. This is very prescient. This is happening right now in your very country where you're testing for COVID antibodies. And the problem is you might get a false positive very often. And as a result, someone may think they've already had it and they don't. That could be scary. It could also be scary if there's a false negative where it's telling you you're fine and you actually have it and don't know it. So that's kind of gets more into type 1, type 2 error. That's something for a different video. Basically, we need to make a tree diagram here. We have to make a diagram of who has this antibody and who doesn't. And if you are tested and it's positive, what's the percent sort of attached with it? So a lot of times it's hard to know how to set this up. So basically, I know that I'm being asked to compare people who have it and people who don't have it. So I'm looking for a sentence that just tells me about having it, not about the positive test result. And that's this one right here. If 10% of the population has these, boom. So that's where I would start. I would start right here and say, okay, 10% of the population has these antibodies, 90% don't. Cool. Now, what's important is that whenever you do a tree diagram, when you branch out, these branches should add up to 1, and they do. Now, I'm about to do a branch out of has antibodies and a branch out of doesn't have antibodies, and the same rule applies. So if I go over here, you were told in this problem that the test correctly identifies someone who has antibodies 80% of the time. Therefore, it must not detect them 20% of the time, because these always have to add up to 1. Sorry, these have to add up to 1. So again, where that came from, you were told 10% of the population has these antibodies, and that you get a positive result 80% of the time when they actually have them. Now, it's important to know when you make a tree diagram, don't just stop there. You have to multiply these. So this 0.1 and this 0.8 need to be multiplied. And that's basically like saying what's the probability you have antibodies and you tested positive? That answer is 0.08. And that's where I got that thing in the table above. Again, you don't need that. That was just me showing you what I did. Okay, now likewise, you want to multiply in this direction as well and get this number. And that describes this top row. Now again, the table, don't worry about the tree diagram. I'm almost positive you probably have to make a tree diagram because it goes along with experimental design and probability. And if your test is kind of like a combination of these ideas into one big question, you'll probably see something like this. So again, setting it up and then multiplying to get each final result will be very important. So now what these mean here, 0.08 or 8% are situations where someone has the antibodies and tests positive. 2% of the time someone has the antibodies and tests negative. Now, moving on, they told you another thing in this problem. They also said to you, you get a false positive 30% of the time. Now, false positive is you start false, but the test says true. So 0.02 is not that. It's right here. That 0.27 is. So how we come about that? If 90% of the population doesn't have these antibodies, but a test is saying it happens 30% of the time, there's the false positive. Multiplying those two gives you a number of 0.27. And then finally, 0.9 don't have antibodies. The test would say they don't 70% of the time, and it would come out 0.63 at the end here. So I guarantee anytime you're doing a tree diagram, there's usually a question like D or E. And here's what D says. What's the probability a patient whose test came back positive really does have antibodies? Now, you don't have to know your fancy formula here if you don't want to. You could probably just show your work. But what I wrote here was the following. They're basically saying this. Given you have a positive test, what's the probability you have antibodies? So given that your test is positive, that's like saying boom and boom. These are the numbers that had positive test. Therefore, the denominator is their sum, or 0.35. Now, the numerator is the, I guess you'd say, combination of those two occurring simultaneously. And that's what's going on in this part. Who has antibodies and tested positive? And that's 0.08. So 0.08 over 0.35 is where I got this answer of 0.229. There will most likely be a question like that when you're doing stuff with tree diagrams. Now, I don't like the way this second one was worded because you were told the probability the test creates a false positive is 30%. So why would they even ask this question? What they were really asking you was this. What's the probability a patient whose test came back positive actually doesn't have antibodies? So that's that 0.27. That's where you would multiply. So the probability the test generates a false positive is 30%. The probability that someone who's tested positive is actually a false positive, you would say, is 0.27. And lastly, it says down here, the FDA doesn't have a treatment unless it has less than 5% false positive. So they need to decrease this by 22%. Now, that idea we'll talk about when we get into, I believe it's Unit 5, when we do Type 1, Type 2 error, where we said you might want to decrease false positive, but it would also increase false negative, and that has to do with the power of a test. And we'll come back to that at a later time. Okay, our very last question, just like the previous one. We're talking about ovarian cancer. Now, again, we usually start with the amount of people who actually have it. And that happens to be in the first sentence this time. So it says 1 of every 5,000 women has ovarian cancer. So that's where we would start. 1 out of 5,000 is the same as 0.0002. And so that's where you branch off to begin with. You'd say 0.0002 have ovarian cancer, 0.9998 don't. Now, you have to read more carefully and see what it says about the testing being done. So, first sentence here says, the test can correctly detect the presence of ovarian cancer 99.97% of the time. So that's like saying you have it and you tested positive. Now you multiply those to get this number over here. All right. And like we talked about before, these have to add up to 1. So if you weren't sure what to put here, well, it's 1 minus 0.9997. Now, like we said before, if you always set yours up in the way I did here, with having and not having as like the two branches and in that order, false positive always lands sort of in row 3, I guess you'd say. Because if false positives occur 5% of the time, that's like saying you don't have ovarian cancer, but you are testing positive there. Now, you'd still multiply those because you want to know the percent of people with positive tests whom don't actually have ovarian cancer, and that's what that 0.04999 means. Okay, so again, don't worry about the contingency table. That will never be required. That was just my way of trying to show you the two and how they work in tandem with one another. But if we move on here, let's use our tree diagram. What's the probability a patient whose test came back positive truly has ovarian cancer? Now, again, you don't have to use the official notation like I did. What this means, though, they're saying if given that someone tested positive, what's the probability they actually have that type of cancer? So this is your denominator. Now, you could have just gone up to your tree diagram and added the two numbers here for that denominator and then said, okay, out of those two, the people who actually have it is this one. So it would be this number over their sum. And that's what you see right here. And it comes out to 0.398%. Okay, so that is Unit 4's study guide, the first half. Again, take time to pause if you need to, fill in anything you see. And if you have any questions, shoot them my way and I'll